Welcome to another deep dive. This time we're tackling this really thought-provoking article you sent in, AI versus Brain, the race for general intelligence.
Oh, yeah, this is a fascinating one for sure.
Right. And it seems like you're really interested in getting to the bottom of, well, how AI actually stacks up against, like, the human brain,
Mm.
What are the real differences here, and why should we even care?
Those are the big questions, aren't they? And I think we're going to uncover some pretty surprising insights along the way.
Absolutely. Like, get this. We're going to talk about how flies, those tiny little creatures, can actually be incredibly intelligent, and how your own brain is constantly learning. Like, it never really stops. And we'll dive into the world of memory and how it's so much more than just, storing data.
Yeah, the whole memory thing is really mind-blowing when you start digging into it. The article itself does a great job of highlighting that even defining artificial general intelligence, or AGI, is kind of tricky.
It's like everyone's using the same label, but talking about different things, right?
Exactly. Even leading researchers like Goldstein, Baker, and Shane, they all have slightly different perspectives on what true AGI would actually look like. It's still a bit of a moving target.
Okay, so let's break that down a bit. What specific qualities do these researchers see as like the hallmarks of AGI? If we could actually point to it, what would it look like?
Well, they point to things like robustness, for one, meaning an AGI would have to be super reliable, not easily thrown off by unexpected input.
So it can't just be good at one thing. It has to be able to handle all kinds of different situations.
Right. And stability, too, as performance would need to remain consistent over time. And then there's coherence, making sure its actions are logical and make sense together.
So it's not just doing things randomly. It has to have some kind of internal logic driving its behavior.
Exactly. But one of the most important aspects, and the one that always seems to trip up current AI, is generalizability. That's the key. Being able to adapt to new situations, apply knowledge across different contexts.
Ah, adaptability. That's what always fascinates me. Like how humans can, learn something in one area and then use that knowledge to solve a totally different problem.
It's pretty amazing when you think about it.
Does that connect to what Shane was saying in the article about memory being absolutely crucial for AGI?
Absolutely.
Yeah.
Memory, in this sense, isn't just about storing information. It's about retrieval and how you actually use that information. It's
Yeah.
all about connecting the dots, making links between different pieces of knowledge.
Oh, and speaking of connecting dots, that's where that crazy fruit fly example comes in, right?
It's catching on. This one's a classic.
Baker, the neuroscientist who studies flies, he argues that these little guys with brains smaller than a pinhead are actually showing signs of general intelligence. They can navigate, complex environments, they integrate all the sensory information, and they control their movements with incredible precision. It just seems, I don't know, almost impossible given how few neurons they have.
It really does challenge our assumptions about intelligence, doesn't it? We often think bigger is better, more neurons equals more smarts.
Right, like more is always better.
But fruit flies are operating with less than 150,000 neurons,
That's it.
while some of the biggest AI systems boast, like millions or even billions of artificial neurons, and yet those flies are still exhibiting more general intelligence in many ways. It's humbling, really.
Okay, so maybe it's not just about the number of neurons. Maybe it's more about how those fly brains are actually organized, how those neurons are connected that makes them so efficient. What is it about brains, like at the cellular level, that makes them so fundamentally different from these massive AI systems we're building?
We got to start with the building blocks themselves. Artificial neurons, the things that make up neural networks in AI, they're really just simplified versions of what's going on in our heads.
Kind of like AI's version of a neuron, right?
Yeah, exactly. But real neurons, they're incredibly diverse and specialized. They use all these different signaling methods, and they form these crazy complex networks that are constantly adapting and changing. It's like a living, breathing city in there.
And always under construction, it sounds like.
Very much so. And it makes me think about how sometimes when you look at AI, it feels very layered.
Yeah, like the information flows in one direction.
Right. Very predictable. But are you saying real brains are more like, I don't know, intricate webs, where neurons have these specialized roles and are constantly communicating with each other in all these different directions?
That's a fantastic way to put it. And if we go back to those flies, Baker's brain scans show all these intricate networks of connections, including these things called lateral connections, feedback projections, and recurrent loops.
Recurrent loops, huh? Those sound intense.
They are. And it suggests a level of complexity and flexibility in information processing that current AI systems, even with all their scale, just don't have. They lack that elegance. Okay, so we've got specialized neurons, we've got these crazy complex connections. What other tricks does the brain have up its sleeve? What else makes it so good at what it does?
Modularity is a big one. The human brain is organized into these specialized functional units, kind of like departments in a company.
Each with their own specialty.
Right. And these modules work in parallel, allowing us to do many things at once, seamlessly. Think about what happens when you're reading a book.
Okay, so you've got your eyes obviously processing the words on the page,
Right.
and then there's some kind of language comprehension going on so you can understand what you're reading, and memory, so you can remember what you just read.
You're getting it.
Yeah.
But there's so much more happening under the hood that we don't even realize. You've got motor control for those tiny eye movements, attention mechanisms filtering out distractions.
Oh, yeah, like when you're trying to read on a bus and people are talking around you.
Exactly. And even emotional responses to the things you're reading.
Right, like when a book makes you laugh or cry.
Exactly. All these modules are working together in the background, in parallel, without you even having to think about it.
It's like a symphony or something.
I like that. Now, contrast that with the AI systems we have today.
So like ChatGPT and all those tools.
Yeah, those are great for certain tasks, but they're largely monolithic. They lack that inherent modularity that our brains have.
They're more like a one-man band than a whole orchestra.
That's a good way to think about it.
Eh,
And Shane and Goldstein, they argue that incorporating this idea of modularity, borrowing from those principles that are used in software development, it could be the key to creating more human-like AI.
That makes sense. Break it down into smaller pieces that can work together. But is it just about the structure, or is there something else going on? Like, how does the way we learn factor into all of this?
You're spot on to bring up learning. I mean, it's one of those fundamental differences between, biological brains and artificial intelligence as we understand it now, at least.
Okay, so walk me through. I mean, how exactly does the way our brains learn differ from how AI is, like, trained? This article you sent had some pretty dense explanations.
Well, think about it like this. Imagine learning a new skill, like shooting a basketball.
Okay.
With each shot, you're watching where the ball goes, right? And you're comparing that to where you wanted it to go. And then, you adjust your technique for the next attempt.
You're constantly tweaking your approach based on what happened before.
Exactly. This constant feedback loop, driven by those error signals, that's how our brains refine actions and get better at things.
So it's a continuous process of like trial and error where our brains are constantly adapting based on the outcome of our actions.
You got it. And the incredible thing is this process isn't just happening when we're, consciously trying to learn something new.
It's like always running in the background.
It is. Every interaction, every experience shapes our brains in ways we don't even realize.
That's kind of wild.
Sure. It really is. It's not just about, memorizing facts. It's about understanding how to learn and how to apply those learnings to different situations, even ones we've never encountered before.
So it's like our brains are always in this training mode, constantly soaking up information, making connections, and just getting better at, well, being brains.
That's a great way to put it.
It makes you wonder if AI works the same way, though.
Well, not quite. The AI systems we have today, they mostly go through these distinct phases: training and then deployment.
Okay.
During the training phase, they're basically force-fed tons and tons of data so they can learn to recognize patterns and relationships.
Like cramming for an exam.
Exactly. But once they're deployed out in the real world, their learning capacity is often much more limited.
So it's like they've memorized all the answers, but if you ask them a question that's even slightly different from what they were trained on, they're kind of lost.
You're getting it. And that's where the brain's continuous learning ability really shines. We can learn something new relatively quickly, and then we just keep getting better at it over time with practice. Plus, we can transfer that knowledge to other tasks, even if they're not exactly the same.
AI systems just can't do that yet.
Not nearly as well. They're much less flexible, at least for now.
This whole idea of continuous learning, though, it makes me think about how we form memories. I mean, AI has memory too, right? Like it can store information.
It can, but it's not really the same as what's happening in our brains, not even close.
So what's the difference? I mean, this Shane guy, the Google engineer you mentioned, he talked about memory being this distributed and multi-timescale thing.
He did. And those are really key concepts when it comes to understanding how our brains work.
But what does that even mean? Is he saying we have like different types of memory working together?
Precisely. We have short-term memory for, immediate tasks.
Like remembering a phone number someone just told you?
Exactly. Then you've got long-term memory for storing, well, pretty much everything else: knowledge, experiences, those kinds of
Or
things.
it's all just swirling around in there?
Not exactly swirling, but these different types of memory are constantly interacting, shaping our understanding of the world, influencing our decisions, even our emotions.
Okay, so it's like when you're trying to solve a problem, you're not just pulling up one specific memory, you're drawing on all these different experiences and bits of knowledge that are kind of woven together in your brain.
Exactly. Think of it like a massive library, right? But with all these different layers of indexing and cross-referencing,
Way more complex than a computer's hard drive.
way more. It's not just about retrieving specific facts. It's about understanding the connections between them and how they relate to the bigger picture. And let's not forget about the emotional side of memory.
Right, how certain memories can trigger feelings or influence our mood.
Exactly. It's all interconnected in ways we're just beginning to understand. And it's this incredible complexity that AI just can't replicate. Not yet, at least. Even the most advanced systems haven't come close to capturing the nuances of human memory or the way it interacts with experience and emotion.
It's mind-boggling, really, when you stop and think about how much is going on up there.
It is, and it makes you wonder if maybe part of the reason AI struggles with this is because it's just not very efficient.
You mean like energy efficiency? I remember reading that even the most powerful AI systems, they use tons of energy, and yet they still can't match the general intelligence of, well, a fly.
It's true. Brains have evolved to be incredibly efficient with the energy they use. They can do these incredibly complex things using a tiny fraction of the energy that our current AI systems require.
It's like nature has already solved the problem of energy efficient intelligence, and we're still trying to catch up.
That's a great way to put it. Maybe instead of just trying to build bigger and more complex systems, we need to take a step back and learn from the elegance and efficiency of, well, the brains that already exist.
So where does this all leave us? I mean, we've gone pretty deep on the differences between how AI and brains work. But what does it all mean for, like, the big picture, the future of AI? Is true AGI even, like, possible?
I think it raises some important questions about how we're approaching AGI in the first place.
Hmm.
Are we on the right track, just trying to build bigger and more complex AI systems?
Just keep scaling things up, throwing more data at it.
Right. Or do we need to, fundamentally rethink our approach? Maybe take some inspiration from how biological brains work, their elegance and efficiency.
That's the big question, isn't it? And this article, it didn't really shy away from that. I mean, Baker, the fly guy, he seemed pretty skeptical that we'll ever be able to create AI that truly replicates what brains can do.
Yeah, he's not alone in that. I mean,
Yeah.
sure, we've seen some amazing progress in AI. There's no denying that.
Yeah.
But we also need to be honest about the limitations of our current approaches.
So maybe just throwing more data and computing power at the problem, maybe that's not enough.
Maybe not. We might be missing something fundamental about, how intelligence actually works.
So maybe we need to shift our focus a bit. Instead of just trying to build like bigger and better AI, maybe we should spend more time trying to understand how our own brains actually work.
I think that's a critical piece of the puzzle.
Yeah.
I mean, it's not just about building smarter machines, right? It's about understanding ourselves better.
And maybe those two things are more connected than we realize.
Exactly. And that brings us back to that thought-provoking question from Baker. If we did fully understand the brain, all its secrets, how would that change how we build AI?
Would we be able to create these super efficient, super intelligent systems that could like actually rival or maybe even surpass human capability? It's kind of a scary thought, isn't it?
It is, but also incredibly exciting. I
Wow.
mean, imagine the possibilities.
Yeah, it really makes you think maybe the goal of AGI isn't just to create machines that can, think like us, but to also use that process to deepen our understanding of ourselves.
I think that's a beautiful way to put it. It's a journey of discovery on multiple levels, both scientific and philosophical.
Well, that's about all the time we have for today's deep dive. We covered a lot of ground, from tiny neurons to the mysteries of memory and the quest for AGI. I hope you've come away with, I don't know, a sense of awe for just how complex and incredible the human brain is, and maybe a more nuanced view of the challenges and possibilities of AI.
It's been a fantastic discussion, and I encourage everyone listening to keep thinking about these questions, keep exploring. The future of AI is still being written, and who knows what amazing discoveries await us.
Until next time, stay curious.